We'll start off the afternoon with Simon DeDeo of Carnegie Mellon.
All right. Thanks very much for joining me in the after lunch doldrums. So I will try to raise your blood sugar, but if this isn't making sense, have a candy bar. So I'm going to talk this. Obviously, it's extremely flattering to be part of such an august group. And it looks like the two talks this afternoon will be focused a lot on mathematical knowledge. So I think Emily will be approaching these questions from a very different angle, but the summary of the point of this lecture is on the first slide. Philosophers have been obsessed for a long time by Gödelian incompleteness, the things that are true but we cannot prove to be true. My claim is that these are essentially mathematically irrelevant unless you're into that sort of thing. But there are other gaps in how we perceive and understand mathematical truths that are far more relevant, not just to the practice of mathematics, but to the very understanding we have of physical and natural law. I was texting with a friend of mine who I've labeled here just as a legitimate philosopher. He is a legitimate philosopher, and some of you know him. He has a book on Kant and a book on metaphysics coming out. And so I was sort of telling him what's going on. He says, look, don't be too impressed by philosophers. We have terrible arguments, but we're really good at big ideas. So don't worry about the arguments. And so in this talk, I'm going to present you a big idea. I'm not going to say my arguments are airtight. But if you take something away of use for your own work, I'd be thrilled. So the formal title of this talk is Hard Proofs and Good Reasons. It's based on a paper written by the mathematician Tim Gowers, who asked this really provocative question: what makes mathematicians believe unproved mathematical statements? So the Riemann hypothesis, probably true. Like, we used to make fun of mathematicians as a physicist, right? Like, our questions, we don't know what the answer is, right? Like, what is dark matter? I don't know. Mathematicians already know the answers to their questions before they begin. Like, you can look at the millennium problems in mathematics and, they'll be like, does this differential equation have a future singularity? And the answer is no. They already know. And their goal here is, in fact, to prove that truth. There seems to be a bizarre sort of anti-correlation. The more certain you are of the truth in mathematics, the harder it is to prove, which is, again, sort of the opposite that we have in at least the physical sciences. So Tim is trying to make sense of how mathematicians work in terms of their intuition, and he talks about things like this. He calls it the no coincidence principle. And he says the more surprising a truth in mathematics is, the more likely it is that there is a good reason for it to be true. And in fact, there's a scaling here. So the more unexpected the truth, the sort of more trivial and obvious the good reason for it to occur. So I thought about this. I talked to a lot of colleagues, in particular in the computer sciences, and ended up writing a paper called Hard Proofs and Good Reasons. So let me first talk briefly. What do mathematical proofs do? What's their job in life? Sometimes we have this perspective. It's a bit of a Platonistic perspective, which is, we go out there, we perceive mathematical truths, like by like ascending some kind of Socratic ladder. We talked about the Symposium, right? Like, you have some, sort of beautiful figure that guides you from the contemplation of beauty into the contemplation of eternal truths. And then you come back down to earth and you're like, look, I know this to be true, right? But now I've got to prove it, right? So this is one idea, that proof is basically just, certifying stuff that you already knew by some other special faculty. So, physicists think they have this faculty. Um, Mathematicians, I think, and if you actually look at mathematical practice, mathematical proofs actually seem to play a very different role. I take a lot of inspiration from Lakatosh's book, Proofs and Refutations, which looks at proof making as a form of dialectic or a form of argument. And in the end, what a proof ought to do is explain and provide reasons why the theorems are true. Without the proof, there are no reasons why. A good proof reveals those reasons why. So there's a kind of weaker version here, right, which is, if you can perceive a good reason for something to be true mathematically, that ought to provide a guide to producing a proof, and potentially vice versa. If you have a good proof, that should reveal the reasons why. Roughly speaking, there's no sort of special faculty that we have to perceive the pure truths of mathematics outside of proofs. This is a proof-first epistemology of mathematics. For some of you, you love math, so this slide is sort of unnecessary, but like, why should we care about a discipline that is in fact incredibly niche? Right? So even at very elite universities where students are rather unconcerned about getting jobs, for Harvard, for example, only 5% of the students major in proof-based mathematics. So like they're roughly the size of the classics department, right? But why should we care about what is essentially, it's a long project. It's been around for 2,500 years. It will keep going, but it's extraordinarily niche. Why do we care? One way to think about this is how we get to some really basic questions in human understanding. So on the one hand, like what is life, what is thought? On the one hand, we gather evidence, we go out into the world, we look at things, and then we sort of make sense of it, right? We do some kind of sense making on the evidence we have. I would say we understand this like really well. We understand how evidence comes into our brains and how we sort of update our priors in response to that. There is what we call the Bayesian revolution in cognitive science, and basically just tells you like here's how to grind through. Like you have some theories about the way the world is. It works great for understanding visual hallucinations. Ryan, I think, gave us some really lovely examples from his work. Um, so we sort of understand the mathematics. The problem is that this task of taking observations, updating our beliefs in this sort of iterative cycle, this hermeneutic cycle of life, is computationally really hard. So in order to invert that conditional, first of all, you got to mentally simulate the consequences of your theories. And then if you're a physicist, you call this thing on the bottom the partition function. This is very hard. So computationally, it might be trivial to state the task, but actually doing the task, actually making sense of the world is extraordinarily hard. And we have yet to really understand this. I think this is probably the next decade in cognitive science. We can grind out papers on Bayesianism forever. I think we're done, right? It's great to train undergraduates. But the real challenge is, can we have a principled understanding of how the resource limitations of the mind affect things? So here's just an example from, I'm in Santa Fe right now. If you've ever been to Santa Fe, there's these flat roofs and you go to sleep and at night you hear like this pitter patter on the roof and it's always a bit disturbing. You're like, what the hell is this? Because they're used to peaked roofs where you don't hear these things, right? So you're like, oh God, what is it? Is it a burglar? Is it a squirrel? Is the roof about to collapse? And you will have all these thoughts if you visit us, right? In order to understand that, you have some gigantic causal graph here, right? That's representing your knowledge about the world. There's all sorts of free variables that you have to trace over, right? Going backwards through this graph, right, is extraordinarily hard. You can translate this, and this is your first complexity class, your computational complexity class. This is in what's called sharp P. This is a very difficult task for machines to do. So understanding how proofs work is part of a project of what I would say is getting a grip on mental efforts. So the 20th century, you might say this was the century of understanding language. So Wittgenstein says the limits of my language are the limits of my world. The 21st century, I would say the limits of my computational resources are the limits of my world. So this project is something that integrates questions in cognitive science, questions in computer science and pure mathematics, very beautiful, and also, interesting enough, economics, the only subject that seems to really handle how to allocate resources when they are finite. So computational complexity, what is it? For the physicists, this is the least transparent explanation I could possibly come up with. Computational complexity is a gauge theory of mental representations, all right? So the change of gauge, these guys call it the Karp reduction. Another way to think about it, and I was thinking about Sandy's talk earlier, she talks about, Descartes, undertakes these representational changes. All of a sudden, we can do geometry better. Computational complexity says what laws of thought are actually invariant under representation change. So if you ask those questions, and we only began to ask them in the 60s, remarkably enough, the Soviets and the Americans did it sort of simultaneously. There are questions that come out from engineering. There are questions that come from science, and there are sort of these really deep questions. In engineering, it's stuff like cryptography, one-way functions. If you've made money on Bitcoin, you should feel bad about it, but you did well. All of these depend upon the fact that some functions, it's really hard to go one way and easy to go the other way, right? Taking derivatives is easy. Integrating functions is hard. There's an asymmetry here that doesn't come out of the time asymmetry, but, let me suggest that maybe some of our understanding of the arrow of time might be enriched by the fact that some functions are easier to go in one direction than another. So a sort of gossip I heard from the quantum computing people is one way to understand why you can't get out of a black hole is that the circuit that you pass through is really hard to invert. Kevin Zollman talked about game theory. Coordination in games is a computationally hard problem. Malcolm and Nick, I can sort of look at their work from this same perspective. Planning and search is hard. And I'll talk today about reasoning and explanation. There is this sort of beauty question sitting in the corner. The questions in computational complexity, the underlying questions like P versus NP, are extraordinarily beautiful. They're probably the hardest questions that we'll ever face as scientists in this era, at least. There's a general sense that P versus NP might be a little bit like string theory. It's like a 23rd century question that was dropped into the 20th century. So mathematics is a great test case, and I'm thinking here about like actual math now, like the math that like math people do, right? And in particular, proof-based math. It's paradigmatically mental. We have to grasp the ideas. It's non-contingent, right? So there's not like you go out and do an experiment and validate your theorem. That is, well, I do that, but that's why I'm not a mathematician. It's actually quite widespread, so we can do psychological experiments on this. People tend to, undergraduates can grasp logical, connectives, for example. And it gets really weird. And if I have time, I'll talk a little bit about like some of the ultimate weirdnesses, mathematics kind of on the edge. So who here, raise your hand if you've heard the phrase P versus NP? Wow. Okay. So most people have it. Some people haven't. That's fine. I'm going to crash course you on P versus NP, and then I'm going to teach you what co-NP is. Very niche. Melanie knows what co-NP is, but many of you won't. So I love detective stories. If you read a detective story, what do you have at the end of the story? You have a bunch of facts, and in fact, they're facts you're not sure about. So some of the facts that you think you know aren't true, and you sort of know, you catch on that some of these things might not be true, right? So what you have in the story, the woman who's writing it, Agatha Christie, is writing the story. She set up a bunch of facts. So at the end of this, right, the detective shows up and he says, all right, look, we have been told the Countess lost her ring. Mr. Snopes chased the thief. The professor says he encountered the maid in the library. The carriage arrived on time. And using, yes, my little gray cells, I can actually compose these inductive events into a set of deductive constraints. And so the Hercule Poirot says, and this is a little bit nerdy math notation here, it's like, it could not be the case, my friends, that the Countess didn't lose her ring and Mr. Snopes chased the thief. That doesn't make sense. One of these two things must be true, right? And, right, it cannot be the case that the Countess lost her ring and, the professor did not encounter the maid in the library, and so on. So what we get here is a deductive problem that emerges out of the inductive world. This is called SAT, or satisfaction. I have set this problem up. There is only one solution here. X1 is false, X2 is false, X3 is false, and X4 is true. I hope that's correct. I haven't double-checked it. Finding this solution is a classic example of what we call NP. This is a problem in NP. It's a problem in NP because it might be hard to find the solution, right? But once the detective tells you the solution, it's really easy for you to check. And you can check it, in fact, in this case, in linear time. You just go clause by clause, and you're like, Mr. Poirot, you said that X1 is false, so it looks like, yes, I can do that first clause. And you've said that X3 is false, so yes, I can do the second clause. It's very easy to verify, but of course, we're all stunned. So there's this kind of beautiful production of something that can then be really efficiently checked. So this is a certificate, right? Here's a slightly different problem, right? So at the end of this, let's say it turns out like, I have ground through all this, X1 false, X2 false, X3 false, X4 true, and that means, Mr. Snope, you are the murderer. Now, Mr. Snopes might say, hang on a second, is there another solution to this, right? Is this the only way to arrange the facts? And in fact, like the detective then has to say, no, in fact, this is the only solution. You must have done it. They usually leave this out of the story, right? And that's because this problem is not in NP, it's in co-NP, okay? So to prove that this puzzle here only has that one solution, you now have to add that solution and negate it and say this has no solutions, okay? To prove that is something in what we call in co-NP. I actually have to produce a mathematical proof, and there is no guarantee that that proof is short. That proof could actually blow up exponentially. right? Co-NP, and I'm told I shouldn't say this, co-NP like feels harder than MP. They're kind of dynamically opposed things. In MP, it's really easy to appreciate the solution. In co-MP, it may not be, right? So some examples, if you're familiar with some of these kinds of problems, right? Traveling salesman, find a path that's of length less than L among all these cities. That's hard, right? That could take potentially exponential time. But once like Sean has found the path for us, right, to the like wander all around the room, to check that it is done is easy. I just literally look at his city pairs and add up the distances. For co-NP, there's no guarantee that appreciation is easy, right? So a co-NP traveling salesman problem would be something like prove there's no path shorter than L, right? In order to give you that proof, that may be exponentially long, right? Intuitively, like maybe what I have to do is literally just show you, look, that one, no, that's longer, that's longer, that's longer, and go through every possible iteration, all right? So what that means is that there are proofs potentially, right? And this is just propositional logic now. There are proofs that may not be good that I just know it's still there. Take this little Hercule Poirot puzzle. To prove that this only has one solution, it turns out like with some very simple proof schema, like there are 4 possible proofs in what's called natural deduction. And depending on how you do those proofs, some proofs are slightly shorter than others, right? So they call them proofs from the book, right? So if I cut on x2 or x3, if my proof focuses there first, I can actually get to the solution faster. So what the intuition here now is that somehow the shorter the proof is, the more sense can be made of the underlying truth, right? So there's some, and so this is this wonderful book that sits in the SFI library called Proofs from the Book. I think this was, who is the guy who did Erdos? Thank you. He's sort of this idealized thing. Every mathematical truth had this sort of most beautiful proof that was like the most insightful, the most economical, that allowed you to perceive the true reasons behind, right? So in this case, in my little silly example here, you can imagine the detective finds the sort of trivial proof or the shorter proof, and he says, look, the professor, he's just a distraction. Really, we have to focus here. And that's how you can see that, in fact, indeed, so-and-so, there is only one solution. Mr. Snopes, you did it. So let's imagine, this is what I call the Goldbach nightmare conjecture. So if you've heard about the Goldbach conjecture, it says every even number larger than 2 is the sum of 2 primes. This is one of these things, if you ask mathematicians, it is widely believed to be true, right? So this is something that Gowers would say, yeah, definitely GC is true. There's lots of statistical evidence, right? And it's not just like, me doing chi-square tests, like it's actually, there's some deeper reasons here. There's a weaker version that was proved in 2013, right? So there's lots of reasons, right? And another way to put it is, if it's false, there better be a really good reason, right? So this is the no coincidence principle. It's the Tim Gowers no coincidence principle. I think of this as like a variation of Leibniz's principle of sufficient reason updated for finite minds. It's not just that there is a reason for everything, but also that reason is comprehensible to us, right? So that God sort of loves us in some way. So here's the Goldbach nightmare, scenario. So you wake up this morning and you check, you go on Number Theory Archive, and you see this paper, right? And here it is, right? This number is not the sum of 2 primes, right? From the Google Goldbach Consortium, comments, like 1 page comments welcome. There will be comments, right? And like the proof is literally just cycle through all 10 to the 16 prime numbers less than that number, right? And show that, for all the primes less than those numbers, the remainder is not prime, right? It's not quite exponentially long in n, the final like disproving object, but it is super polynomial. I would say this is a mathematical truth with no good reason. This is an unreasonable truth. It's provable. It's not some weird Gödel thing, right? But it is something that we cannot comprehend, right? So computational complexity will tell you that, in fact, at least in propositional logic, hard proofs like this, right, mathematical truths that are true with no good reason are dense. They're everywhere, right? There are many, many proofs, right? Or there are many, many theorems whose proofs scale exponentially in the length of the statement, right? So the Goldbach nightmare scenario would be one example. It's not true. Don't check it. It's not true, right? But the general law of the field is most theorems are true for no good reason, right? So it's this joke, right? Like physicists think they're God, right? God thinks she is Agatha Christie, right? Somehow the problems that we're getting set, or the ones we tend to encounter, tend to be the ones that we can prove. So here are a few other examples of, in this case, finite truths without reasons. So two coloring the Pythagorean triples. Pythagorean triples, integer triplets, where the two squares sum to the third square. You can think of it like, here's this object. Can you color this object so that all the edges are, that no triangle has like the same colors on all these edges? You can do it up to n of 7,825, and then it fails. The only proof we have is a 200 terabyte CoMP proof that just shows you, I mean, it's very intelligent. It doesn't exhaustively check. But you might say this is like a reasonable structure with unreasonable properties. So I don't want to call this lawless ontic structural reason, right? So there are lots of things like this. Some of them are a bit like game-like, but this one, Terry Tao actually attacked it and found a reasonable proof. There's Jeremy Avogad, sort of, he saw my paper, he said this only applies to propositional logic. What about logic over, sort of infinite things like the set of all integers? So here's a few examples. This is kind of a fun one. You encounter the Goldbach conjecture. There's the weak Goldbach conjecture, which has now been proved. Before it was proved, so here it is again. Before it was proved, this very clever person, Zinoviev, in 1997, had the following theorem, which he published. Okay, assuming the generalized Riemann hypothesis, fine, just give him that, right? Every odd number greater than 10 to the 20 can be written as the sum of 3 primes, and he can prove that in a kind of elegant way. And then some dorks checked all of the numbers below 10 to the 20, and they're all fine too. So I have now proved the weak Goldbach conjecture. So this is a kind of interesting hybrid case here, a little bit like the four-color theorem, if you remember those debates, where in the end, I think we will crack it, right? Human knowledge will continue to expand. But these are the kinds of things, as you're exploring the space of theorems, you're generically going to run into. So if that's true, if you buy this story, then you now have this problem like, why does it, like, Tim Gowers is no fool, right? Most mathematicians, I think, when they read Tim's paper and said, yeah, things are true for a reason, right? So for example, right, you're trying to prove a theorem, you need this lemma, it's like, you want to prove A implies C, and there's this thing B, and if B were true, like A implies B and B implies C, and then you're just set. So you look at B and you're like, should I try and prove it? Well, is it true? And you're kind of going on these reasonableness vibes, right? So Tim says this is what we do. It's part of the practice of mathematics. So why does it work? So the obvious answer is it just doesn't work, right? There are many mathematical truths that are true for no good reason. And in fact, we encounter them all the time. Mathematicians will continually run into them, and they will perceive a mathematical truth. They can't see the reason for it, right? And so they will assume it's not true. They won't assume they'll just kind of avoid that part of the space. So you think about this a little bit in terms of Neeman's argument about playing out, all of your notation in some basin of attraction. Now what you have is a basin of attraction with these like bizarre resistances that are kind of cognitively impenetrable to us, right? One thing you might say, so some mathematicians tell me this, is like, yeah, absolutely, I buy it. They're unreasonable truths, but like I have great taste as a mathematician. And I mean, they don't say it that way, right? They say, great mathematicians have great taste. And they somehow like are able to weave around them. They can see, don't pickaxe in that part of the space, right? So that would be nice, but it turns out that can't be true either. So being able to perceive the length of a proof ahead of time would actually be a kind of oracle that would give you magical powers that you probably don't have, right? So that actually can't be true, right? If there is intuition, right, it can't actually it can't actually give you that kind of intuition unless like crazy things like P equals MP are true. I can't remember exactly which thing collapses, but this is probably not true, right? To assume mathematicians have the ability to only encounter theorems that have reasonable proofs, they just can't, right? I think this is probably true is in fact we do, right? As we are trying to prove things, or as people better at mathematics than I do try to prove things, right? They continually encounter these things, right? They're using certain kinds of heuristics, right? So they think, for example, oh, like I can't see a reason for A not to be true, right? So it's probably true, kind of Gowers intuition. They kind of grind away at it for a while, and then they just are like, oh, like I'm just not as good at math as I wanted to be, and they give up, right? And in fact, that thing was true, right? But they couldn't, like, the proof was in fact inaccessible to human mind, right? So this is where we end up. This is our picture, kind of the dark matters of mathematics, all mathematical truths, right? And all provable mathematical truths, right? So the 20th, it's like, Doug Hofstadter is in the red zone here. Like every grateful, like Daniel Dummett wrote stuff, Putnam, they were all writing about this. It seems to, I've never encountered a mathematician, for example, who says, yeah, I was trying to prove this lemma, but it might have been one of those Gödelian unprovable truths, right? That would sound unbelievably pretentious to a normal mathematician. So, here's all provable truths, right? So the yellow, right? Here's all efficiently provable truths. So these are things potentially true for a reason, right? Sitting in here, right? These are all truths whose proofs relate to human perceivable reasons, because of course we emerge out of a culture, right? So some reasons are sort of more accessible to us. Some proof strategies are more accessible to us. Um, One thing people sort of want to know is like, what is AI going to do here? Obviously, AI is going to find things that are they're sort of in that light blue zone, right? AI is going to potentially find shorter proofs. So there's some really interesting work at CMU right now on this. So Chase Norman, who's working on I mean, this is quite beyond me, but working on ways to find efficient paths to proofs. And you look at these proofs that the machine makes, and it's like, wow, like a human would never put induction there, right? Like, don't do induction that deep in the tree. And like the machine's like, oh, this is actually like really efficient. You also wonder, like, AI is, like we do actually solve NP and co-NP hard problems all the time, right? We just, the machine grinds away. So it may, in fact, we may end up with lemmas that we know are true because we trust the compilers, right? We can't understand them. These are like axioms that are just unbelievably bizarre. They're a little bit like the, oh, the Pythagorean triples can't be two-colored after 7,285, but we'll never really understand them. They'll never be part of our cognitive artifact. We're playing around. I do empirical work because obviously I can't do mathematics. So we've been looking at how people explain mathematics to each other. So we scraped the Institute for Advanced Studies pure mathematics talks. It's really easy to spot them, right? Like if I know if I've accidentally gotten a physics talk because they look very, very different. The ways that mathematicians actually explain things is incredible. So one problem like you have, and like if you ask me like, why does the W boson have this property? I'm like, oh, because the Higgs fell into this little potential. And I can imagine a world in which the Higgs didn't do that. But you can't imagine a world in which the Pythagorean theorem is false, right? Causal explanations are usually how we explain things. There's no causality in mathematics. So oftentimes what you end up with are these beautiful cases where mathematicians sometimes invent like a kind of fool, like a little bit like Galileo in his dialogues on natural philosophy, where it's like, look, you might think X, but notice that if you thought X, it would lead you down this road and you'd be a fool. So therefore, that is why not X. Right? That's a epistemically relative reason to a fallible human subject. So we get that. There's some talks are like this. So, and I notice the younger people tend to do these talks. They're much easier to understand. And then you get other people, and they just sort of like throw things up on the board, and they're like, look, A and B and C. And they just keep doing that for the entire talk. And you never actually perceive an argument. It's almost like they're drawing your attention like to different parts of mathematics. And I think it's a little bit like wayfinding, right? So they're not really explaining things, but they're kind of guiding you through almost to reproduce their own cognitive process. I'll talk briefly, I have just a minute, a little bit about cognition on the edge, right? So I promise we talk about very weird mathematics. My French is terrible, let's put it that way. Alexander Grothendieck, probably one of the most unusual mathematicians, on Nema's scale of like how voluble you are. And like, he's very voluble. He sort of isolated himself from humanity, but wrote thousands of pages of kind of crazy stuff near the end of his life. So Reapings and Sowings coming up from MIT Press. I have to read it sort of very slowly. But Grothendieck is somebody right on the edge, right? So if most facts in mathematics are unreasonable, right, what is it like being out there? You're always constantly bumping into these things, right, that are true, but for no perceivable reason. And Grothendieck talks about this. I'll say there's a continual and uninterrupted back and forth movement here between the apprehension of the thing and the expression of what has been apprehended by way of a language that has been refined and recreated as the work unwinds under the constant pressure of immediate needs. So one way to say this is there's a kind of coevolution here between the objects, the things the theorems are about, and then the reasons or the proofs, right? We're not just, 1700s, it's like, let's prove stuff about curves that, you won't stub your toe on, right? Now the objects that we're proving things about are moving along with the proof. So it reminds me a little bit, if I think about Nima's lovely talk yesterday, right? Shut up and calculate, meaning the notation is smarter than your verbal reasoning, but at the same time, it's like you should feel the winds in the basin of attraction. We don't quite understand how the things we want to know and the things we have reasons for are moving together. That is precisely where I should end. Thank you very much.
Thanks, Sean and Janan, for organizing this fantastic workshop. And also thanks especially to Quinn and Danielle, the administrators in the philosophy department, who've really just done like a fantastic job. Yeah, so I don't know if I can live up to the we're supposed to have big ideas as philosophers job description that Simon set for me in his talk. But my plan is just to kind of recapitulate in a way that might be helpful and separate two different questions in the epistemology of mathematics that were raised in the talk that I thought were very interesting. And then to talk a bit about this question of how the lengths of possible proofs of mathematical claims is related to all of this. So I'll raise a couple questions about whether the connection is maybe exactly as tight as was suggested in the talk and in this diagram where the efficient provability of truths is parenthetically identified with there being a reason for the truth of that claim, or at least a connection between those two statuses is suggested. Okay, so the first thing I wanted to say is just to talk about a certain sense in which there might be no coincidences, or we might know that there aren't coincidences in mathematics. So for example, we might know that Goldbach's conjecture isn't true by coincidence, or that if Goldbach's conjecture is false, the fact that it's true for, up to very large natural numbers, that pattern isn't true by coincidence, or it's failing when it does isn't somehow just coincidental. And why is that a particular puzzle, or why is it a distinctive puzzle in the case of mathematics, unlike in empirical science? So in a callback to the previous slide, where there was Bayesianism, the thing we understand very well, and then the epistemology of mathematics, or mathematical proof, where we're more in the dark. The reason there's a challenge here is that the way we're usually used to thinking about knowing that there aren't coincidences in, say, empirical science is we imagine a space of possibilities, and we have some probability distribution maybe over these possibilities, or some extra structure on these possibilities. And there are certain possibilities where the coincidence obtains, but there's something about those possibilities that allows us to rule them out. Maybe they have low probability, maybe something else allows us to know that they don't obtain. That's the kind of epistemology that I tend to work on. I don't work really in the epistemology of mathematics. So for example, how could you know that a coin that landed heads 100 times in a row is double-headed rather than a fair coin that landed heads 100 times in a row by coincidence? Well, maybe the possibility where it landed heads every time by coincidence is sufficiently improbable or sufficiently abnormal that we can be confident or even know that that's not how things are. We can't reason in the same way, or at least it's very hard to know how to reason in the same way about coincidence in mathematics because of the non-contingency of the truths of mathematics. There just aren't genuine possibilities where the truth of Goldbach's conjecture is other than it actually is. So that's one set of puzzles. How can we, it seems like we need new tools to think about how we can know, say, that if Goldbach's conjecture is true, it's not true by coincidence. We can't, in an obvious way, repurpose the tools we have from, say, knowing how if a coin's going to land heads 100 times in a row, it's because it's double-headed rather than fair. And it's not just that there's this further project. I think it's also a puzzle because it doesn't feel like the epistemology of these two kinds of things is, so radically different. It seems like in both cases there's some common thing, believe that it's not going to happen by coincidence. And how can we make sense of what the commonality is between these two things, given these sorts of challenges and reconciling the foundations in terms of one being a contingent subject matter, the other being a non-contingent subject matter. Okay, there was a different kind of non-coincidence issue that was raised in the epistemology of mathematics, though, and I just want to recapitulate it. Maybe that would add some value, make it stick, because I think it's such a gripping question, which is the puzzle sort of alluded to in this diagram. How is it that mathematicians are so good at math? How is it that they end up working on problems that they can solve, right? Now you might think, oh, well, they just start with the axioms and just prove stuff from there, kind of blindly. And so of course, they end up, proving theorems, because that's just where the theorems come from. Of course, mathematics doesn't proceed in that way. And if mathematics proceeded in a different way, if mathematicians were just sort of randomly picking formulas in set theory or arithmetic or whatever and trying to figure those out, well, there are general reasons to think we're probably going to end up in the Gödel zone sometimes. We're going to end up with stuff where we don't have any strategy for proving the things. And the kinds of things you might think could be out there to give us guidance, like, oh, select a random claim and do a test to see, well, if there's a proof, it's not too long. And then if it's not too long, then try and prove it. Well, the problem is, again, there is no such algorithm, or at least if P is distinct from NP, I take it, or something close to that, there is no such algorithm. And we believe there's no such algorithm. So what is it exactly that's guiding us, or guiding mathematicians towards problems that they can solve? Problems that seem interesting independently or compelling, that's a filter for the kind of problems people work on. And then also through doing mathematics, there's accumulated knowledge and as a field and knowledge that individuals accumulate, through education and working with mathematical things, working on mathematical problems and so on, where they get a sense, they develop heuristics for what are the kinds of questions that are going to be tractable. And I think there's just a question like, what exactly could that be, given these impossibility results, that there aren't algorithms that can let you know in advance that if it's provable, it's tractable in the sense that the proof isn't too long. Okay, two things about the length of proof. One is some of the claims about proofs being, say, exponentially long. I'm not sure that those statuses really make sense as claims about particular proofs, right? So for a particular class of proofs, like traveling salesman problems or these SAT problems or whatever, that you can ask, like, how does the length of the shortest proof of these things scale as the thing we're trying to prove or the thing we're trying to find gets longer and longer? But for a particular theorem, like that just has a proof which is however long it is. It's not, it's not exponential in any kind of sense. And moreover, the kinds of theorems that mathematicians are interested in are not things that in some natural way fall in some kind of reference class of things. It's like, oh yeah, we proved, Fermat's last theorem 17, but that's part of the large class of theorems like Fermat's last theorem n, where, the proof of all of those grows exponentially. So I'm not sure what length of proof as characterized in these ways to do with efficiency or exponentiality and so on, what that really comes to in the case of proving a particular thing. But let's just prescind from that and think about the intuitive notion of like, that proof is really long or that proof is really brute force. I'm not sure how connected that is to whether there are, in just some intuitive, ordinary sense, reasons that the thing is true, or whether we have understanding or something satisfying there. Fermat's last theorem has a really long proof. And it's not just that the proof is, long in some kind of absolute terms or like relative to the cognitive powers of human beings or pieces of paper or so on. It's very long, at least the proofs we know of, in comparison to how compactly you can state the thing which is proved. So that sort of relational notion of length of proof, which came up in the written version of Simon's paper, which you can find on the archive, is there. And I don't know. I don't think that means that there's no good reason why Fermat's last theorem is true, right? I think people are very impressed with Fermat's last theorem, not just as a feat of, I don't know, mathematical brute force or firepower that Andrew Wiles had, but in terms of what it revealed about the structure of number theory and different areas of mathematics being put together in a way which felt like we were seeing all sorts of reasons for all sorts of mathematical facts being true. And I think it's also helpful to think about edge cases, and in particular, the edge case of Gödelian incompleteness, where there aren't any proofs to be had, at least within the given formal system that you're thinking about. But it's not clear that we don't have knowledge, and I think it's even less clear that if the relevant claims are true, they aren't true for reasons. So, for example, think about the consistency of arithmetic. That can't be proved within arithmetic, assuming arithmetic is in fact consistent. I think we know that arithmetic is consistent, and I think if arithmetic is consistent, there's a good reason for that. It's a little bit further to say that we know that, say, Zermelo-Fraenkel set theory is consistent, but I do think we know that actually. And I think if it's true, there are good reasons that it's true. So there are other things that have shorter proofs or longer proofs that I could riff on, but what is really short is time, so I think I'll leave it there. Thanks.